All right. Hi, everyone. Thank you for joining us today. I know that we're competing with Earth Science Division Town Hall. But we're here and we do appreciate you coming. So we have a couple of folks online as well. And so thank you for your participation. Yesterday, you all had the opportunity to participate as well in the ICESat-2 mission town hall. That was hosted by Laurie Magruder, who's the science team lead, and Tom Newman and others from the mission. And there you got the opportunity to learn about all of the exciting ways in which folks have benefited from the measurements coming out of ICESat-2, and the different tools and opportunities that are available to explore the data. In this town hall, we're going to focus on the quick look products that were released by the mission in March of 2022. And the goal for today is to create a conversation about, the needs and the requirements that drove their development, as well as the use that is starting to develop from the data products. And so I'm going to switch here. Let's see. So we have a great lineup of speakers today. We're going to start with our own Molly Brown, who's the ICESat-2 application scientist. Molly has been working on assessing user needs and the need for low latency since the early 2000s. So we're going to start with a quick intro from Molly on what is data latency. In a second, and then we're going to move to Tom Newman, who's going to talk about the current status of ICESat-2. Just a quick overview. I know that he went over that yesterday, so just a brief overview, but really focusing in on the quick look products and the data tools that are available to explore this from the National Snow and Ice Data Center DAC. We also have with us Tian Zhao joining us from NASA's ASP Lands. She is the coordinator. And this is NASA's land atmosphere near real-time capability for Earth observation, for the Earth observation system. So she's going to give us an overview of the collaboration that happened to develop this quick look data products and how you can get involved in discovering the data products via LANS. We're also joined by Pontus Olofsson. He is the project scientist for the Satellite Needs Working Group. And so there is a stakeholder engagement program from the SNWG, and Pontus is going to let us know how you can participate in that or how does that work. And of course, the Quick Look products were developed jointly with the SNWG. We're going to get an overview of that. We've also invited two of our applied users that represent the communities that really drove the need for the low latency data products. Dr. Huiling Gao from Texas A&M University, talking about Western reservoir monitoring and how the low latency data products can work for that. And also from the U.S. National Ice Center, we're joined by Ludovic Brooker, who's the chief scientist. He's going to give us the context for this need at the NSID, at the U.S. NIC. And we also have our applied user, Hongye Xie, joined by his student, Yong Hyun Koo, who are going to talk about their work to inform the US NIC ice charts with the low latency data products. Hi, Huiling, you can come here. Thank you. So we're going to start with Molly Brown. And we don't
have to speak very quickly so that we can fit everyone in. So data latency, as you probably know, is the temporal gap between when the satellite acquires the image from space and the user is able to download it onto or access the data for themselves. So that includes the amount of time it takes for the satellite to go through space to a downlink station, and then travel from that downlink station to central processing, then be processed, right? And then, which in ICESat-2's case that's the biggest gap, the amount of time. And then from there, go onto Worldview or other publicly accessible database, and then be posted online. So each one of those steps takes time. In the case of ICESat-2, the most time it takes is for the very accurate telemetry and other details, right, to make sure that we conform with our level 1 requirements. And you can come up here, Tom, and correct anything I just said.
Great. Yep. Okay. Totally. So Sabrina, should I just click on to the next one here? Boop. Oh, escape. This one. Awesome. Cool. Just a couple of slides. Yeah, many of you would have heard this yesterday. Oh, it's not. Thinking about it. Great. And if you didn't hear it yesterday, here's a little bit on the current status of ICESat-2. We've been on orbit for 1,552 days now. I didn't update this by one from yesterday. And of course, the sole instrument on the ICESat-2 observatory is ATLAS. That's the laser altimeter. Everything is healthy up in space, and so I won't belabor the point. ATLAS is doing its thing, up to 1.33 trillion laser pulses and counting. For folks who haven't looked at ICESat-2 data products before, just a one slider, what ATLAS does is transmit green laser light down to the surface of the Earth and generate 6 individual footprints on the ground. And that reflected laser light sends photons back off the surface of the Earth that are detected by ATLAS. And it's those returned photons that form the basis of our data product suite. The biggest one is ATL03, and that's what's plotted here. Each one of those little dots in the figure is the representation of a photon with a unique latitude, longitude, and height. The background gray is, in this case, due to sunlight. This was a daytime pass, and the sun puts out photons in that same part of the spectrum. But of course, the heavy curve through the middle that your eye is drawn to are photons reflected off the surface of the Earth, in this case composed of many tens of thousands or hundreds of thousands of individual photons. Since the product is unwieldy, it's a very large data product because it's got all sorts of parameters at the photon rate. We have a handful of higher level data products that aggregate those photons and post surface height or other characteristics of the Earth at a particular long track spacing typically. And it's these products, the long track products that are unique to each surface type, that we chose to transform into quick look products that we'll hear more about. As Molly indicated, the latency on our final data products that have the best geolocation and the best heights we can do take better part of 2 months typically. But these quick look products don't have all of those corrections and don't have the best and final geolocation, are out in about 3 days, which isn't really near real time, but it is lower latency, substantially lower latency than our final products. And what we heard from working with Sabrina and Molly over the years is that for a lot of users, they don't need that nth level of detail, that if we can get it to them sooner, that there's benefit there for them. Here's the little data product suite. You can get all of these products at the NSIDC DAC. If you just search for NSIDC and ICESat-2, you will find them. At this point, we only have a handful of the data products in quick look form that are distributed through the DAC and are discoverable through Lance as well. But if you have other requests for other products, by all means, let us know. So I spoke to some of this already, but what I'll draw your attention to are the products here in the middle. QL at the end of the product name, like ATL07 QL, indicates the quick look version. The main difference between the quick looks and the final in terms of height are down there at the bottom, as well as the differences in location. And those errors are just due to not using the best and final geolocation we can provide. So in height space, quick looks are lower by about 2.5 meters and less precise. There's a larger spread of those heights. And then you see the long track and cross track errors in position there in the bottom bullet as well. So if you're using ICESat-2 data, you don't have to start from zero. There's a lot of tools out there to help jumpstart your work. And all of these are linked through the NSIDC ICESat-2 pages. One way we found really helpful, if you have the time, is to participate in a hack week. That's a 5-day intensive that's aimed to take you from zero to science using the ICESat-2 data products. The form fit function of the final products and the quick look products are the same. Parameter names are the same. Group structure is the same. It's just the information content is a little bit different, as I described on the last slide. So any of these tools, which were developed for final products, can be used with quick look products as well. Yeah, we've been, ICESat-2's been on orbit for just over 4 years, and we're about to go through our first senior review. That's a process that NASA uses to evaluate and then extend missions that are functioning well and people finding value in the data. And it's a 3-year process. So we'll go through our first senior review next spring, which would, if we're successful, carry us through to October 2026. I should say that the instrument and observatory are both healthy. We don't have obvious life-limiting items. So this is more on the programmatic funding side. Hopefully when we get to October 2026, knock on wood, all will be well then as well, and we can apply to continue. I'll just leave a few bottom lines up here. The green one is the one that I just mentioned. Everything is looking good in space. So if you've been reluctant to jump in with ICESat-2 data, because it does take some time to get used to a new product, to ingest a new product, to figure out what to do with it. We've got 4 years of data now and more on the way. So hopefully it's worth your time. And that's all I was going to say. Cool.
Okay, and we just have, so Tian Jiao is joining us online, and she did a pre-recorded presentation. And just to note, we want to make this a conversation. So after this introduction to Lance from Tian Jiao, we will move into more of a discussion. So thank you. Let's see.
Welcome to my presentation. My name is Tian Yao. I'm a research scientist and ASB Lance coordinator from NASA Earth Applied Sciences program. I'm honored to be here to introduce the NSIDC-TAC ICESat-2 quick look data in NASA's Lens. In my talk, I will introduce NASA's Lens near real-time data system and the new Lens data ICESat-2 quick look data. Let me start with Lens. Lens refers to NASA's land, atmosphere, near real-time capability for Earth observing systems. During the past 13 years, Lens continues to provide data products that are made available much quicker than routine processing allows. The Fire Information for Resource Management System, or FORMS, is a part of Lens. FORMS is being used to track wildfires and smoke across the US and Canada. Lens is managed by NASA's Earth Science Data and Information System. Lens managers are Karen Michael, Diane Davis, and Jenny Hewson. As one of the primary users of Lens data, NASA Earth Applied Sciences program promotes the use of Lens data in time-sensitive applications. Dr. David Green is a Lens scientist in Applied Sciences program. Led by Dr. Miguel Roman, a user working group is responsible for providing guidance and recommendations to Lens. The user working group meets at least once a year to share the updates from each Lens elements, provide feedback from users, and also review the proposals to bring new near real-time capability to Lens in order to make sure that Lens meets the needs of users in near real-time community. Lens products are routinely used by direct users and also by brokers who add values to the data. As I mentioned before, NASA Applied Sciences program is one of the primary users of Lens data which collaborates with partner organizations, provides support to research scientists to discover and demonstrate applications of NASA Earth science, research and technology to solve problems and make better decisions. The Applied Sciences program promotes the use of LANS data and builds a bridge between application users and research teams. Next, I'm going to introduce NSIDC-DAC ICESat-2 Quick Look data. In collaboration with the Impact Project, the ICESat-2 Quick Look data is now available in LANS in addition to the NSIDC-DAC. It's a joint effort by Impact, ICESat-2 SIPS and the Science Office, NSIDC-DAC, and LANS. The ICESat-2 Quick Look datasets were created to fill needs for low latency data for mapping sea ice, surface water extent, and vegetation height. This need was identified through the Satellite Needs Working Group's 2018 assessment survey. LANS provides ICESat-2 Quick Look data as early as 72 hours from satellite observations, much faster than the typical processing period required for ICESat-2 standard datasets. The Ice, Cloud, and Land Elevation Satellite 2, or ICESat-2, collects elevation data over all surface spanning the world's frozen regions, including forests, lakes, urban areas, and many more. Currently, ICESat-2 Quick Look datasets include the sea ice height, land and vegetation height, backscattering profiles, and atmospheric layer characteristics, sea ice freeboard, and inland surface water data products. This data will support users and applications, including sea ice forecasting, vegetation height, surface water, and flooding monitoring, as well as land surface deformation from landslides and volcanoes. So how to access data? First, you need to register for an Earth data login profile, and then users could search and download ICESat-2 Quick Look data from NSIDC-DAC system or the Earth Data Near Real-Time website. Just FYI, on Wednesdays, NSIDC-DAC system typically have maintenance, and access to ICESat-2 data might not available. LANS generally provides ICESat-2 Quick Look data within 3 days of satellite observations, in comparison to an average latency of 60 days for the standard ICESat-2 data products. In early 2023, ICESat-2 data will version up from version 5 to version 6. Related information will be emailed to registered users and also will be available on a data set landing page and Earth data website. If you are interested in ICESat-2 datasets, please subscribe to mailing list on the NSIDC-DAC landing page to receive email updates. Thank you very much for your attention. If you have any questions or comments, please feel free to contact me. Thank you.
All right, thank you so much, Tian. And we do have folks online. And so I think next we're just going to have a discussion on just the Quick Look product. And so we have various guests with us today. We can start with Pontus Olofsson, which I mentioned is the program scientist for the Satellite Needs Working Group. And so Pontus, I think if you can tell us how you worked with the mission to develop a Quick Look product, and maybe how everyone here can participate in satellite working group to communicate those needed improvements.
Yes, thank you very much. Is this on? Oh, okay. That's better. Yeah, so the satellite working group was mentioned in the previous presentation here. And so I just want to mention one thing before I talk about that. So before I joined NASA Marshall as a civil servant, which was quite recently, I was funded by the carbon monitoring system, just like Molly's been for many years. And one thing we did with that funding was to map above ground carbon in tropical forest, and we used ICESat data for that. We used old glass laser shot from space, and later on JEDI, and also looking at the ICESat-2 data. And so that's a very different kind of application than we're talking about here. And in that research, we were not interested in the latency. That didn't really matter. What matters was the geolocation accuracy, which was very important because we went to the forest and made a measurement of biomass. And then that measurement was done where we had a glass observation. And so now we could relate the above ground biomass as measured with the laser shot. And then we could create a simple model and then get an estimate of biomass for each shot. And then the second step was to scale it up using wall-to-wall reflectance data. So we get a wall-to-wall map of biomass. And now the geolocation area is very important, and the latency is not that important. And so it's just an example of the importance of spaceborne LiDAR data, that it has a lot of different applications. And it's so funny that we're using a satellite called ICESat to monitor above ground carbon in tropical forests. But that's what we did. And it actually worked out very well. We got a few papers in the pipeline explaining how we also can try to track change in biomass using this type of data. So yeah, that's a parenthesis. Now I support something called the Satellite Needs Working Group. And that's it's not something that it's not run only by NASA Marshall. It's a big NASA, USGS, NOAA initiative. And so what we try to do is to get a sense of the Earth observation need among U.S. federal agencies. And that's an important kind of aspect of it. This is only focused on U.S. federal agencies. So every 2 years, we construct a survey and we send that out. The USGS is in charge of that. We send it out to all federal agencies, all civilian federal agencies, I should say. And they communicate their Earth observation needs. And then we do assessments of those needs. So we have interviews with all the people that submitted those needs. And then we try to formulate solutions. And this, again, is a big collaborative effort between the various NASA centers, NASA headquarters, USGS, and NOAA. And then a handful of those solutions are selected by the executive branch of the government for implementation. And in 2018, one of the solutions were these ICESat-2 quick links. Just like was communicated in the previous presentation, that there was a need for, close to near real-time products, and the geolocation error, stuff like that didn't matter too much. And there's been other solutions as well in the 2018 cycle that are being implemented by JPL. They're called OPERA. And they are doing their own stakeholder engagement program. For the 2020 cycle, we changed things a little bit. So now Marshall became in charge of the stakeholder engagement. So we're currently setting up contracts for 4 solutions selected by OMB. And we will do stakeholder engagement with related to those 4 solutions. So one thing we do is that we poll the stakeholders, asking what kind of training data they need, what kind of training needs they have, and how we can address that. And it's quite different because solutions are very different. Some of them are based on HLS data, the Landsat Sentinel-2 data and vegetation indices. Others are very kind of specific atmospheric science solutions. So that's what we're trying to do. When it comes to the 2018 cycle, I actually don't know who's doing the stakeholder engagement for the ICESat quick look. I know that JPL was in charge of all the opera stuff, but the ICESat-2, I don't really know. I should have checked that before this. for the 2020 solutions, it's Marshall, but it's still unclear to me what, because there's no funding to Marshall for the 2018 solutions. That being said, we could still do something. We could still, if there's interest, if there's a need. We are limited to U.S. federal agencies as it is at this point, though. So that's kind of where we stand. We're, by the way, we're right now in the assessment of the 2022 needs that we're submitting. I think, Tom, you'll be part of some of those interviews. So we sit down, we have the interview with each of the people submitting those needs, trying to understand what the actual satellite need is and how we can address that.
Thank you, Pontus. And I think it's important to really grasp how all of this works and how everything comes together in developing this. Are there any questions for Pontus at this point? And for those joining us online, you can feel free to unmute as well. I think it's really great to hear about your use of ICESat-2 data for vegetation in the tropics. And we have actually one of our applied users, Hui Ling Gao, who has been working with ICESat-2, or at least telling us about the potential use for ICESat-2 data for water management. And so you're now exploring the QuickLoop product, and perhaps you can share a little bit about that.
Okay, thanks. So I can start with a little bit background to how I get to use ICESat-2. So I work on remote sensing of lakes or reservoirs, particularly elevation and storage. So in 2014, first of all, 2012, I published a paper looking at using radar altimeters for elevation and estimate reservoir storage. But we can only get to limited amount of locations. Then there are regions like South Asia that there are like water is really important. But when we looked at then 8 years ago, there were like only 2 locations with radar altimetry data. So that's when we started using ICESat. And using ICESat, we were able to get to 2,000 reservoirs. So we started getting interested in actually when I met at the early adopter program, and then trying out the model, the ICESat-2 early data. So basically, ICESat-2 and ICESat in my group, we have been working on parallelly. And one thing like our previous speaker talked about, we started with using just a regular, not worried about the data latency, primarily to use ICESat or ICESat-2 to develop the relationship between the elevation and the surface area so that we can parameterize to estimate the storage variations, just to use area estimations, which is a lot easier to get from Landsat. So ICESat-2, what we found, I want to compare ICESat-2 with ICESat, is that there are 2 things. I think one is the technical part, the accuracy is a lot better. The other thing is the ground tracks. I want to mention is that a lot more ground tracks. So with that, when we look at these bathymetry or area elevation relationships, we are able to cover most of the global lakes and reservoirs. That helps a lot with water management. So currently I have through the water resources program, we are developing a reservoir monitor and forecasting system for the Western US, with the drought. And our agency primarily work with us is Bureau of Reclamations. And even with Bureau, not all reservoirs, the elevations mattered. So that's where we come in, like we want to use remote sensing to help fill in the data gaps. And I started thinking by using ICESat-2 as a way to validate the data. And then, of course, with this low latency, quick data is really exciting because then we can use ICESat-2 to monitor the elevations. Of course, you'll say, like ICESat-2 had this repeat cycle, for so long, but that's why we come back to this, the dense ground tracks. So we look at water body, and if you look at specific track, it takes 3 months to get another measurement. But if you look like, for instance, Lake Mead, there are like so many dozens of measurements. So like the temporal resolution can be increased. So we haven't really, worked on like using the data for this water management because this is a new project, but I'm really excited about exploring this. And I think, again, ICESat-2, the vertical accuracy, the footprint size, and those are phenomenal. And I think it will also go complement the SWOT very well. Thank you.
Thank you, Phelan. Any questions for Phelan at this point? Molly and Susan? Okay. So I think we'll move to another FFI users. We're joined by Jung Ku and Hong Ye Xie. And they'll be talking about their work with the freeboard data, with the quick look data, to inform the U.S. National Ice Center's ice chart. And they actually have some work already that has demonstrated the potential for this. And so, Young-Soo, I believe you can unmute. Yeah.
Oh yeah, can you hear me?
Yes, we can hear you. And I can pull your presentation here, or you can pull it from over there. Should I do it from here?
Sorry, I cannot hear you clearly, so.
Would you like me to pull up your presentation from here, or can you do it from over there?
Oh, I think I can do here.
Okay, great. Thank you.
Can you see my screen?
Yes, we can see them. Thank you.
Oh, great. Thank you. Yeah, so I just want to briefly introduce about how to improve National Ice Center ice chart data by using ICESat-2 data. So we just want to introduce some potential and challenges. So as other presenters already mentioned, we already have the ICESat-2 quick look data. And especially in this study, I want to introduce ATL10 quick look data, which is sea ice freeboard. And this ATL10 data is about sea ice freeboard measurement. And this data has about 3 days of latency. And actually, the advantage of using this ATL10 data is that it provides the kind of accurate freeboard measurement in numerical values. And our research team also developed a kind of kriging interpolation tool to merge this APL10 product to create a weekly freeboard surface, weekly freeboard map. And this algorithm is just for solving the problem of spatial sparsity of the ICESat-2 track data. So by using this kriging method, we can provide freeboard surface map from ICESat-2 data. And National Ice Center ice chart data is this is an example of the ice chart for the Antarctica. And this data is updated every Thursday. So this is a weekly or bi-weekly data. But as you can see here, the one issue of this product is that it only provides the very brief sea ice stage of development. So it's not a real numerical thickness values, but it's just a rough ice thickness. So it has some ice code of sea ice stage of development. And this thickness value is just very rough value. So this ice chart is very good to see the distribution of sea ice by its development stage, but it cannot provide any accurate thickness values. So our idea is that we can apply this quick look data to supplement this ice chart data, so we can provide more accurate thickness estimation for this ice chart. So this is an example of the comparison between ICESat-2 quick look data and ice chart. So basically, this background is the ice chart, and this is the stage of development. And you can see this bright color is kind of a thin ice, and this dark color is a thick ice. So in this example of the rosy area, there is a kind of thin ice polynya area near the rose ice shelf, and ice chart represents this area very well. And this is the coincident weekly ICESat-2 quick look data for this area. And we also create a surface freeboard map by using this ICESat-2 data. And as you can see here, the ice chart, the polygons of ice chart and the thin ice area or thick ice area from ICESat-2 agrees very well. So by using this quick data with 3 days of latency, we can efficiently supplement this ice chart data by adding numerical freeboard or thickness values beyond the rough ice development stage of the ice chart. However, there are some challenges because this ice chart is created by some visual interpretation from many experts and CS analysts. So we need to consider about how to include this CS freeboard and thickness information from ICESat-2 into this ice analysis workflow. And also we need to assess this output, and also we need to update these standard operating procedures to supplement this ice chart. So that can be an issue, but at least we want to say ICESat-2 quick look data is very good data source to supplement this weekly national ice chart NIC ice chart data. Yeah, so yeah, that's pretty much.
Thank you so much, Yongsu. Let me see if I can. Oh, there you go. You can just get us back to all your faces. Before we go into a little bit more of the discussion of what you have done with Hongye, I do want to give the opportunity for Ludovic Brecker to join us from the U.S. NIC to give us the context for ICE operations. So just a little bit of a background. Our applied users, one of the requirements for applied users is that they have a link to an end use and to a partner. And the partner for Hongye and for their work is basically with the U.S. NIC. And so, Ludo, I was hoping you could give us that context in your environment and tell us about, what excites you about Hongye and Yongkyu's work and about the low latency data products in general. Thank you.
Yes, thanks. Thanks, Sabrina. Greetings all. Happy to share what are the needs of US NIC ICE analysts and the need of our end users. So US NIC is a federal center, so we support every campaign, every operation that is funded by the US government. So we have different kind of users. We have the users who wish to avoid ICE at all cost. In that case, we will provide no ICE information. But we also have users carrying out scientific campaigns on the ICE, or the Coast Guard breaking ICE, so they operate on the ICE through the ICE. And in that case, they have a need for a lot more information about the characteristic of the ICE cover. And when we have people on the ICE or asset in the ICE, what matters is the latency. We shouldn't deliver a product that is already 2 days old. That's why the ICESat-2 reduced latency product is very interesting. And for the first time, it offers us information about the third dimension. So because with ICESat-2, we can get access to freeboard, obviously, but also information about surface roughness, which to us can be translated into ridge heights. So challenges that an icebreaker may face while trying to break the ice. So that is very appealing. Now, there are obviously some limitation in what we can do operationally. So the presentation earlier was interesting, but those changes won't happen anytime soon because we have to follow some requirements, and some of them are set by WMO standards. So we use stages of development. This is per WMO standard, but we can supplement information with a different product adding thickness. So I will leave it at that. If you have another question, I'm happy to touch about an ongoing work with the ICESat-2 Project Science Office.
Thank you, Ludo. I'll open it up here for questions from folks that we have here.
Yeah, maybe for Ludo. Ludo, you mentioned, and we saw in the slides that the real variable that you're interested in is the thickness, and of course, ICESat-2 primarily lets us derive freeboard. Would you find value in estimated thickness, say using a snow climatology model, or would that be too coarse yet, and you'd need something more refined than that?
So freeboard for now is fine. What matters is latency. So if running an algorithm to get to thickness adds time, then it decreases value. So interestingly, I had a call this week with the crew coming back from the Arctic, who was on the Hilly, and what matters to them is really knowing the ridges, knowing the state of the snowpack, and then thickness matters too. But they couldn't agree among themselves whether thickness was more important than the ice stage of development. They prefer to know at first glance whether it's seasonal ice versus older ice that is harder to break. Also, what matters to them is the flow size, and we can get that from ICESat-2. We can get a flow size distribution. So to your question, whether freeboard is more important than thickness, unclear at the moment because our end users are not used to receive thickness information. So it will take another year and a half before I can get that feedback to you.
Thanks, Ludo. That's really interesting. So it sounds like if there was a way to add a ridge height parameter or assess that ridge height parameter, that might be the most useful thing we could do, provided that it didn't increase the latency.
Yes, and that is what is exciting currently, thanks to the Project Science Office at Goddard and Nathan Kurtz and Marco Beniardi. So I talked with Nathan and Sabrina last week. I received a prototype gridded product, so a 5-day gridded product at 2.5 kilometer resolution with freeboard and roughness for the Ross Sea. And I was able to share that product with the Coast Guard icebreaker Polar Star that is currently in Australia, departing to McMurdo on Wednesday next week. So they have acknowledged already a reception of the product. They will look at it. And that's the first time they will have access to such a product. So looking forward to debrief with them. We will hopefully continue to share that product every few days and see how useful it is for them in order to do two things: to identify a route. And for them, an ideal route is a path of least resistance. So thinner ice, more opening, easier to navigate, but also to do some tactical decision. So at some point, I will start to monitor the ship position with the overlapping ICESat-2 tracks to see if we can transition from a gridded product to a long track product and see if that adds value to them. What is new as well is for the first time, they have access to Starlink internet connection. So data bandwidth will not be a limitation. Back to you.
Oh, that's very cool. Thanks, Ludo, for that extra context. Really interesting stuff.
Yeah, so I think in moving forward, maybe Clayton, if there are other parameters that are of interest, from your research that you think could improve the fitness product, that would be feedback that we could give to Tom, to the satellite needs working group. As well as here, are there other parameters that the ICESat should consider for the fitness product for your type of application? And I know there are other types of applications here that could be of potential. So if you want to share those with us, we welcome your comments here.
So going back to the kind of forest carbon monitoring. One program that I've been involved in quite a bit is called Silva Carbon, which is a capacity building program of the U.S. government. And I think it's managed out of USGS headquarters. Funding comes from USAID. The State Department is involved. NASA has been involved as well. The U.S. Forest Service is very active in Silva Carbon. And one thing we do, one of the kind of key goals of Silva Carbon is to assist countries report carbon emissions associated with deforestation, forest degradation. Tropical countries that can show that they're reducing such emission can get economically compensated. And so what we've been doing is doing workshops and training and stuff to use data like ICESat and JEDI and ICESat-2 data, such that countries can themselves use that data to estimate carbon emissions. One thing that is really helpful in that context is if the data is available on things like Google Earth Engine, for example. That makes the country's life much easier these days. So I'm just wondering, what's the plan? Are you guys working with Google? Because I don't think the Atlas data is on the engine, right? Is there a discussions?
Yeah, there is. Yeah, actually, just this fall, we were in touch with a Google engineer who was beginning that process for ATL08 in particular, the vegetation canopy type product. And yeah, I've heard from a few folks at this meeting that they'd really benefit from having the other products available in Google Earth Engine as well. So we'll definitely be following up on that.
Yeah, the JEDI data is available, for example, and that's been, it just increased the use of the data. So I don't want to push either way, but I think, if I speak on behalf of a lot of the kind of stakeholders in tropical countries that I've been working with, that's something that they really request and benefit from.
Yeah, I just want to echo on this. Having that data on Google Earth Engine will be wonderful because, for instance, our work, we use lots of Landsat data. So it's like everything go on the cloud. If we can process and handle simultaneously, that will be wonderful. Because right now, our work, we download all the tracks and locally in the processing. And to me, that type of time can be saved, especially, for the low latency. Thank you.
And I know we have Tian as well. And so I wanted to ask you just a little bit more about how folks can engage with Lens. What are their opportunities? I know you mentioned you provided links to how folks can access the QuitLoop products via Lens. Are there other ways that folks can interact with you? I think you are unmuted, Tian.
Can you hear me now?
Yeah.
Yeah, great. So the next Lens UWG meeting gonna be in June 2023 in Wisconsin-Madison. So if anyone interested in attending the meeting, please feel free to contact me and I can tell you more information about it. And also there is a monthly telecom, Lens Element telecom. So each month we have a tech-up meeting, just to communicate from the each Lens element, including ICESat-2 QuitLoop data, and also with other near real-time data like MODIS, VIIRS, and others. And the worldview gives. So yeah, if anyone interested, feel free to join it, and we can, we want to learn what you need, what's your near real-time needs, and also what's the new opportunity for low latency data. And also we want to learn more about which applications you are interested. And we want to identify the gap in current Lens data system. Yeah, thank you.
Thank you, Dan.
I'm not sure who could answer this, but is there any idea of the bias that the near real-time products have over the regular products? And can you just say a few words about the differences?
Sure, I could add some more words about that. Yeah, as I mentioned, the quick look products don't have that best final heights or geolocations. There is a bias. The quick look products are lower by 2.7 meters, and you can just add that back on, or we can work to do that. But for many of these applications, like canopy height or like freeboard, that doesn't matter because it's a differential measurement, and that absolute drops out. So it also has a larger uncertainty, so a wider precision, more spread of the photons about the surface, and the locations aren't as good. For some applications, that's a real challenge, others a little less so. The geolocation uncertainty of the final products is plus or minus about 3 or 4 meters, but for the quick look products, it's about 10 meters in the across track direction and up to 100 meters in the along track direction. And that's due to the imprecision of the knowledge of where the observatory is in space. Of course, the ICESat-2 observatory is moving very quickly, 7,000 meters a second. And so if you're off by just 1/10 of a second in your solution, that's 700 meters. So it's better than that. But yeah, those are the major differences.
Just keep that in mind, folks, when you're using this stuff.
And I guess I'll just ask, a lot of the operations, a lot of the applications, of course, depend on the continuity of the mission. And I always get that question, how long will ICESat-2 run for? And also, how can applied users in just the applications community contribute to the extension of the mission?
Technically, the instrument and the observatory are both healthy. Often fuel is the life-limiting item for these missions. How long can you stay in the orbit that you need to be in to collect those data? And we're seeing that now with the Aqua, Terra, and Aura missions that are 20+ years on orbit. For ICESat-2, our latest fuel projections would carry us out to about 2036. So that's a long ways from now. The instrument itself is healthy, and we do continue to watch for any trends or any degradation of the instrument. But that's all been healthy. That's good. Of course, space is hard. We could get hit by a Starlink tomorrow or something like this. But barring disaster, all is well at the moment. Funding for these missions is that 3-year senior review cycle that I mentioned a little earlier. So while technically things look good, programmatically we go through that review every 3 years, and certainly feedback on applications and different users is part of that review. So whatever feedback you have, we're always welcome to hear it.
And in terms of submitting that feedback for the next senior review, Tom, is there a deadline where we can provide you the feedback from the community?
Yeah, we haven't gotten that schedule yet, Sabrina, but when we do, you'll definitely know it, and people will be sending you that feedback that will then go into the review package. So yeah.
And in terms of the satellite working group, is that something can compose directly with the satellite working group? What is sort of the process for the federal agency?
Yeah, we're sending out surveys every 2 years, and so people are free to communicate all the needs they have, and especially if it's related to active remote sensing, LiDAR, spaceborne LiDAR observation. That's all important, and the more that is being communicated, the more we can advocate for it. I think when it comes to spaceborne LiDAR data, there's so many different types of applications, and you see that with just the ICESat glass data, which didn't operate for very long, right? We don't have a whole lot of data, but the amount of research that we've done with just that relatively limited amount of data is pretty spectacular. And so having routine collection of spaceborne LiDAR measurements is extremely important. And so if we can do anything in Satellite Working Group to advocate for that, we're more than happy to do it.
We're nearing the time of the end of our town hall. yes, you can come up and talk to all of our wonderful speakers here. Thank you so much for coming, for taking the time to join us today. Have a great evening. Apologies, we did have a comment from Tian. Tian, did you want to say something? I think she was there. No, I think we missed it. Okay. Yeah. Thank you everyone so much.